All right, in this video, we will be going over section 5.6. Section 5.6 is about improper integrals. Okay, basically, we are going to learn how to integrate functions which are not continuous at certain points. I want to start with this definition, definition 5.19. Suppose A and B are any real numbers and f of x is a function. Okay, we have three parts. Here is the first part. If f is continuous on the interval a comma infinity, notice that a is included, then definite integral from a to infinity f of x dx is equal to limit as b approaches to infinity a to b f of x dx. So what you do is you replace this infinity symbol by uppercase b, and then you take the limit b approaches to infinity. Okay, as b approaches to infinity, this will be going to infinity, and it looks like you get this integration back. Okay. All right, and then by the way, this kind of a integral is called an improper integral because infinity is involved there. Okay, whenever there's an infinity plus or minus infinity involved, that's going to be an improper integral. Here is the second part. If f is continuous on the interval minus infinity comma b, b is included again, then the definite integral of f of x from minus infinity to b is defined as limit as a approaches to minus infinity a to b f of x dx. Okay, the definite integral from a to b f of x dx. As you can see again, as a approaches to infinity, this will be going to infinity. Then you get your original integration back as a approaches to a minus infinity. All right, here is the third part. If f is continuous on the interval minus infinity comma infinity, then the definite integral over minus infinity comma infinity as a sum of two cases splitting at any real number c. So basically, we need the definite integral. This definite integral, as you can see, this is an improper integral because infinity is involved. So how do you write this as a limit? What I do is I take a point between minus infinity and infinity. I'll call that point c. This is your real line, of course. And then I integrate from minus infinity to c and then c to plus infinity. That's what I'm going to do. Okay. Then when I do the integration from minus infinity to c, I can write that integration in this form. Okay. Limit as a approaches to minus infinity, a to c f of x dx. Okay. Definite integral limit as a approaches to minus infinity, definite integral from a to c f of x dx. This will take care of this minus infinity, okay? Because as a approaches to minus infinity, this will be minus infinity. And then for the other part, from c to infinity, I can write that as the limit of this integral, okay? Definitely, to take the limit as b approaches to infinity, the definite integral of f of x from c to b this time, okay? So you can write this improper integral as the sum of two limits this way. And in each of these cases, we say that the improper integral, this improper integral is convergent if this limit exists. In this case also, we say that this improper integral is convergent if this limit exists, similarly for the third part. Next, I want to go over definition 5.20. Let's see what the definition tells us. If a and b are real numbers, any real numbers, and f of x is a function, here is the first part. If f is continuous on a comma b, b is included, a is excluded, but not at x is equal to a. It is not continuous at this point. Then the definite integral of f of x from a to b is written as limit as a approaches to uppercase of a approaches to a from the positive side, the definite integral of f of x from uppercase a to lowercase b. Okay, see what happens here. This is the troubling point. A is the troubling point because my function is not continuous at a. So what I do is I take this limit uppercase a approaches to a plus and put your lower limit to be the uppercase a. As a approaches to lowercase a from the positive side, this becomes a, right? You get this original integral back. Again, if this integral exists, we say that this improper integral converges. Okay, again, here also this integral is improper because your function is not continuous at x is equal to a. And then the next part, if f is continuous on a comma b, this time a is included, b is excluded, but not at x is equal to b, then this definite integral of f of x from a to b is defined as limit as uppercase b approaches to lowercase b from the negative side, the definite integral a to uppercase b f of x dx. Okay, so that's how you define it. As you can see, as b approaches to a lowercase b from the negative side, this becomes b. Okay, so you get back this, you get back your original integration. And then here is the third part. If f is continuous on a comma on the intersection of these two intervals. Okay, notice that c is not included in the interval in the intersection of the interval, but this a and b are included. If a is continuous on the intersection of these two intervals, but not at x is equal to c, then we can define the integral over a comma b as the sum of the first two cases. Okay, so what you do is you take the definite integral from a to b f of x dx to be the sum of these two limits. Okay, limit as b approaches to c from the negative side, the definite integral of f of x from a to uppercase b plus the limit as a approaches to c from the positive side, the definite integral of f of x from a to uppercase a to lowercase b. Okay, that's how you define it. All right, again, in these cases, we have improper integrals because my function is not continuous at least one point. So they are improper integrals. We say that those improper integrals are convergent if these limits exist. If this limit exists, we say that those improper integrals converge. All right, let's move on. Let's look at this example. Express each improper integral that follows as a sum of limits of proper definite integrals. Do not calculate any integral or limits, just write down. Okay. So we need to write each integral as a sum of proper definite integrals. Okay, so how do you deal with this one? First of all, notice that, let's work on part A. First of all, notice that this is 0 to 1, 1 over 3x minus 1 to the power 2 over 3 dx. Okay, in this case, clearly at x is equal to 1 over 3, we have a discontinuity. This integrand is not continuous at x is equal to 1 over 3. So we need to, I'm going to split this integral at x is equal to 1/3, and I'm going to write two integrals first. Okay, so I'm going to write this as 0 to 1/3. That's the point where the integrand is not continuous, over 3x minus 1 to the power 2/3 dx plus now 1/3 to 1. Remember, you have to go up to 1 divided by 3x minus 1 to the power 2 over 3 dx. Now I can apply my definitions. Okay, at this point, my function is not continuous, so I can write this improper integral as a limit of a definite integral. Okay, so this is what I'm going to do. This is equal to limit as a approaches to 1/3 from the negative side, 0 to a, the definite integral of my integrand from 0 to a. Dx, that is the first integral. The second integral becomes limit as b approaches to 1/3 from the positive side, the definite integral from 1/3 to 1 over 3x minus 1 to the power 2 over 3 dx. Okay, that completes the first part. We wrote this improper integral as the sum of the limits of two definite integrals. All right, let's move on to the next part. Actually, before we move on to the next example, you might be wondering why I put a approaches to 1/3 from the negative side here. Okay, notice that this is the integral that we want to write. So your values are x values are between 0 and 1 over 3. So your a value should approaches to 1/3 from below. So you are going from 0 to 1/3. That means you are approaching to 1/3 from below. So that's why I put minus sign here to indicate that you are approaching from the left hand side. Here clearly again here in the second case you are approaching to 1 from the right hand side because you are coming from 1 to 1/3 this time. So your b is approaching to 1/3 from the right hand side. All right, now let's work on the second example. So how do we write the second one? As the sum of two definite integrals, two or more definite integrals. Well, first of all, notice that in the second one, in this interval of integration 0 to 1, you have 2 points at which your function, your integrand is not continuous. One is at x is equal to 0. Clearly at x is equal to 0, your denominator is 0, it's not continuous. And also it's not continuous at x is equal to 1 because at x is equal to 1, ln 1 is 0. Again, you have a 0 denominator. Okay, so how do we write this definite, this improper integral as a sum of proper definite integrals? What I'm going to do is I'm going to take a point between 0 and 1 and I'm going to split this integration. Okay, so my original integration 0 to 1 over x ln x dx should be equal to 0 to 1/2. You can take any that point to be any point. Okay, I'll take 1/2. Integration of x ln x dx plus, and then I integrate my function from 1/2 to 1. Integration of x ln x dx. Now I can use the limit statement using definition 5.20. Okay, so I'm going to write the limit definition here. So this should be equal to limit, in this integral 0 is the troubling point, okay, because my integrand is not continuous at this point, so I have to put the limit for this one. So I'm going to write limit as a approaches to 0 from the positive side, integration a to 1/2 1 over x ln x dx. That's the first integral, and then the second integral will be limit as b approaches to 1 from the negative side, definite integral 1/2 to b 1 over x ln x dx. Okay, so we have written our original improper integral as a sum of two proper definite integrals. All right, that completes that example. All right, next we have this particular integral, part C. Integration 0 to infinity 1 over x minus 2 squared dx. Okay, so notice that my integrand is not continuous at x is equal to 2. At x is equal to 2, I have a discontinuity. Okay, so I'm going to split this integration into two pieces first. So this integration will be equal to integration 0 to 2 1 over x minus 2 squared dx, and then I integrate from 2 to infinity. 2 to infinity, And now when I write 2 to infinity, let me first write this one actually. 2 to infinity, 1 over x minus 2 squared dx. Notice that in this integral, both these points are troubling point. The infinity is a troubling point because it's infinity. So it's an improper integral. And 2 is also a troubling point. So in this case, I'm going to split this integration again by taking the middle point. I'm going to take a point between 2 and infinity and then split my integration into 2 pieces based on that number. So this is going to be equal to integration from 0 to 2, 1 over x minus 2 squared dx plus integration 2 to 3. I'll take that middle number to be 3. Okay, if you want, you can take that to be 4. That's fine. 1 over x minus 2 squared dx plus the last one, I'm integrating that from 3 to infinity. 3 to infinity, 1 over x minus 2 squared dx. Now I can use the limit definition. Okay, in definition 5.19, I can use this. I can write my improper integrals as proper integrals using these definitions. All right, so let me write this as sum of proper integrals. How do you handle with this one? Notice that here, this is the only troubling number. X is equal to 2 is the troubling number. So I have to use a limit for this one. What I do is I replace this by a, and then I take the limit of a. Okay, so I take limit as a goes to 2 from the negative side. It is approaching to 2 from below. That means from the negative side. A goes to 2 from the negative side. 0 to a, 1 over x minus 2 squared dx. And then my second integral will become, again, notice that this is the only troubling number. So I have to replace this by b, and then take the limit of b as b approaches to 2. So you have limit as b approaches to 2 from the right hand side this time, because your b is here. So your b should be approaching to 2 from above. Okay, so that means it's from right hand side because you are in the interval 2, 3. The definite integral of f of x from b to 3. So f of x is of course x minus 2 squared, 1 over x minus 2 squared dx. And my last integral will be limit as a approaches to infinity, 3 to here we cannot use a actually because I already used a. So I will use a different symbol here. I'll use c. Uppercase c approaches to infinity, 3 to c, 1 over x minus 2 squared dx. Okay, that completes that part. We wrote our original improper integral as a sum of proper definite integrals. Okay. All right, let's move on. Next, I want to go over this theorem 5.21, improper integrals of power functions on 1, infinity. Okay. All right, so let's see what the theorem tells us. If p is between 0 and 1, p is greater than 1 and less than or equal to, if p is greater than 0 and less than or equal to 1, then 1 over x to the power p is greater than or equal to 1 over x. Okay, you can check this using a graphing utility whether this is true. Okay, for all x in x between 1 and infinity, and in that case, this improper integral, the definite integral of 1 over x to the power p from 1 to infinity diverges. Okay, and this is the second part. If p is greater than 1, then we can show that 1 over x to the power p is less than 1 over x for all x in this interval. And this improper integral, the definite integral from 1 to infinity, 1 over x to the power p dx, converges to this particular number. Okay. Notice that in this in each case, this is the shape of the graph. This is the shape of the graph in green when your p is between 0 and 1. And here is the shape of the graph in black. In black, when your p is bigger than 1. Okay, as you can see, this tells you that this integral converges. Integration when p is between 0 and 1, that means you are in this situation. P is between 0 and 1 means this is your graph. Okay, what does this mean in that case? What does this improper integral means? That is the area under the curve 1 over x to the power p on this interval 1 comma infinity. That is this area. This area. Okay, this diverges means this area is infinite. That's what it tells you geometrical. And then if you go to the next part, when p is bigger than 1, this is the graph. When p is bigger than 1, this is the graph of y is equal to 1 over x to the power p. In that case, this definite integral converges. That means the area under this curve on that interval is finite. That's what we mean by convergence. This area is finite. Okay, so that's the geometric interpretation. All right, let's move on to our next theorem, theorem 5.22. This time we are going to be focusing on the interval 0, 1. Remember, in the previous theorem, we focused on 1, infinity. Now on the interval 0, 1. If p is strictly between 0 and 1, then 1 over x to the power p is less than 1 over x for all x in this interval, and this improper integral converges to this particular number 1 over 1 minus p. P is this number, okay? P is this power. And then if p is bigger than or equal to 1, then 1 over x to the power p is greater than or equal to 1 over x for all x in this interval. And in that case, this improper integral diverges. Again, here is the geometry. Notice that this time we are focused on the interval 0, 1. Okay, this is the interval that we are interested in. If p is strictly between 0 and 1, here is the graph in green. Okay, y is equal to 1 over x to the power p. This is the graph. And if p is bigger than or equal to 1, this is the graph, the black graph. Okay. All right. In this case, if p is strictly between 0 and 1, then this improper integral converges. Okay. That means, what does that tell you? What does this improper integral mean? That means the area of the green graph under the curve on the interval 0, 1. Okay. So when p is strictly between 0 and 1, this is the graph. This indefinite integral, this improper integral means the area under that curve on that interval 0, 1. That is this area. This area. Okay, that area is finite. And then if p is bigger than or equal to 1, here is the graph. In that case, it tells us that this improper integral diverges. What does that mean? That means this area is infinite. Area under that black graph on the interval 0, 1 is infinite. But the previous one convergent. Okay, it converged. That means the area under the green graph is finite, and the area under this black graph is infinite on that interval 0, 1. That's what it tells you geometrically. All right, let's move on. Next, I want to work on this example. By the way, all these parts are same, so I'm going to work on only one of them. The other parts are very similar. First of all, let's read the example. For each power function f of x that follows, use limits of definite integrals to determine whether f of x, the definite integral of f of x from 0 to 1 dx and definite integral of f of x from 1 to infinity dx converge or diverge find the values of those improper integrals which converge. Okay, let's work on this one. I will work on only on part A. The other parts are very similar to part A. Okay, the procedure is exactly the same. Okay, so let's work on the case, this case. Let's deal with this improper integral 0 to 1 f of x dx. So we need to, part A, we need to decide whether this particular improper integral is convergent or divergent. Okay, first of all, I want you to notice that this is 0 to 1, 0 to 1, 1 over x to the power 1/3. Cubic root means 1/3 power, right? In the problem, we are asked to use limits of definite integral to determine whether this is convergent or divergent. And at the end of the day, you need to find the value of this improper integral. But if you are not asked to use the limits of definite integrals, then there is an easy way to solve this, answer this question. To determine, there's an easy way to determine whether this is convergent or divergent. What is that easy way? The theorem that we learned. See, 0 to 1 interval. This is the theorem for the 0 to 1 interval, 0, 1 interval. In that case, all you need is, notice that this function, this your integrand, takes this form. Okay, 1 over x to the power p, with your p value is 1/3 in this case. 1/3 means it is strictly between, your p value is strictly between 0 and 1. So you are in this case, that means this is the conclusion. This improper integral converges to this value. Okay, since your p value in this case is 1/3, which is strictly between 0 and 1, we know that this converges. Okay, this converges. We can in fact find the value of that. That value can be found using this one, 1 over 1 minus p. So your value would be 1 over 1 minus p. P is 1/3. This is, of course, if you simplify this, you will get, what would you get? 3 over 2. Your answer would be 3 over 2. But that's not what we are asked to do here. We are asked to use the limit of definite integrals to find this one. Okay, so at least we know the answer from the previous theorem. Okay, so with that answer, let's see whether we come up with this answer. All right, so let's use the, let's write this improper integral as a sum of proper definite integrals. Okay, so what I'm going to do is, I'm going to rewrite my integration 0 to 1. I want 1 over x to the power 1/3 dx. I'm going to rewrite this as, remember the only discontinuous point, only point where your integrand is discontinuous is x is equal to 0. So you need to put the limit here. So I'm going to replace my 0 by a and then leave the other limit as it is. I'm going to write my integral. And then I need to put the limit appropriately. Limit as a approaches to, definitely a should approach to 0. Now the question is whether it is from the left hand side or the right hand side. Remember, you are on the interval 0, 1. You replace your 0 by a. So you are approaching to a from above. That means you are approaching to, your a is approaches to 0 from the right hand side. So you need to have a plus sign. Okay, so now we have written our original improper integral as a proper definite integral, limit of a proper definite integral. Now all you need to do is to calculate this definite integral. Let's do that. I'll leave the limit outside. Limit as a approaches to 0 from the positive side. I know how to integrate this function. Okay, the integration of this function will give you, you know, basic rules now to integrate. So the integration will be 3 over 2 times x to the power 2 over 3, and then you need to put the limits, of course, a to 1. let's find this limit. This is going to be limit a approaches to 0 from the positive side, 3 over 2. If you plug in 1, you just get 1 to the power 2 over 3, which is 1, minus 3 over 2 times a to the power 2 over 3. This is what you get. Okay. Now you take the limit. Limit as a approaches to 0 from the positive side. As a approaches to 0 from the positive side, this piece will go away. So your answer is 3 over 2. Notice that you get the same answer as the answer that you got using your theorem. What theorem was that? Theorem 5.22. The answers are same. Okay. All right. We are done with that one, but we need to find the other integral. We need to determine whether this integral is convergent or divergent. Okay, let's work on that. Perhaps I will copy that integral to the other side. All right, here is the integral that I need to deal with now. Okay, this time it is 1 to infinity. You need to find this improper integral. Improper integral of f of x from 1 to infinity. So this is what we need to calculate. Okay. Again, notice that the bad point is infinity. Okay. Infinity is the bad point here. This function is continuous everywhere else on the interval 1 comma infinity. Okay. So 1 is also a good point. So I need to deal with this one through a limit. So I'm going to write my integral as a limit. Limit as a approaches to infinity, I'm going to replace this infinity by a. Definite integral 1 to a 1 over x to the power 1/3 dx. That's what I have. Okay, I replace this infinity by a, and then I take the limit as a approaches to infinity. That's what exactly I want. I want this to go to infinity to get this integral. Okay, now I have a definite integral, proper definite integral. I can calculate this one. Okay, if I calculate that, of course, I can use the previous calculation. This is going to be the integration of that integrand. So this is equal to limit a approaches to infinity. You have 3 over 2 times x to the power 2 over 3. You need to put the limit. The integration of this function is equal to this one, and then you need to put the limits here. Here you should have a, this is 1, and if you evaluate this one, you get a goes to infinity. You plug in the upper limit, 3 over 2 times a to the power limit, 3 over 2 times 1 to the power 2 over 3, which is just 3 over 2. Okay, so that's what we have. Now, all you need to do is take the limit as a approaches to infinity. What happens to this limit as a approaches to infinity? Clearly, as a approaches to infinity, since this is a positive power, this part will go to infinity. This is a finite number. So the whole thing will be approaching to infinity. This will be infinity. Okay, that means my integration, this improper integral is divergent. So we write 1 to infinity 1 over x to the power 1/3 dx is divergent. Okay, notice that you can determine that this is divergent using the theorem if you want. Okay, but in this case we are asked to use the limits. That's why we use these limits ideas to determine whether it is convergent or divergent. Okay, notice that your p is 1/3. If you go to the theorem, which is on the interval 1 comma infinity, here is the theorem. This improper integral diverges if your p is between if your p is greater than 0 and less than or equal to 1. So we are in that case. In this case, your p is 1/3, which is between 0 and 1. In that case, according to that theorem, this improper integral should diverge, and we get that result using these limit arguments. All right, as I said, the other two parts are very much similar to the first part. So I'm going to leave those two as an exercise for you, okay? All right, here is the next example I want to go over. Use limits of definite integrals to calculate each of the following improper integrals. All right, let's work on the first part, A. 0 to infinity, e to the power minus x. Let me first actually write it. That is actually equal to, yeah, first of all, notice that on this interval, what is the problematic point? Would the function be continuous at 0? Yes, it is continuous at 0. Okay, if you look at the graph of e to the power minus x, you will see that the graph looks like this. Okay, as you can see, it's continuous everywhere. So this is the only improper point. Okay, so you need to write this integral as a limit of some proper definite integral. Okay, so this is going to be equal to limit as a approaches to infinity, 0 to a, e to the power minus x dx. That's how you write that as a limit of proper definite integral. So you replace your infinity by a, and then you take the limit as a approaches to infinity. Okay, as a approaches to infinity, this will become infinity. That's what you need. All right, now I'm going to deal with this proper integral, proper definite integral. Let me calculate that. This is going to be equal to limit a approaches to infinity. I know how to integrate this function, e to the power minus x. Okay, we have seen this function before. So integration of that would be minus e to the power minus x. Of course, you need to apply the limits 0 to 1, 0 to a, pardon me. And then if you compute this evaluation, you can evaluate this by plugging the upper and lower limits. You get a approaches to infinity minus e to the power minus a minus, notice that when you plug in x is equal to 0, you get minus 1, right? So that minus and this minus will become plus 1. Okay, that's what you get. Now you need to find this limit. You take the limit as a approaches to infinity. Notice that e to the power minus a is nothing but, this is nothing but 1 over e to the power a, right? You can bring the term to the bottom to make the exponent positive. This is same thing as 1 over e to the power a. Now, as you can see, as a approaches to infinity, this becomes infinity. That means 1 over infinity. This takes the form 1 over infinity. It's going to be 0. Okay. So you get 0 plus 1, which is in fact, let me actually write this way. You get here minus 1 over infinity plus 1, because this takes the form 1 over infinity. With this minus sign, it becomes minus 1 over infinity plus 1, which is clearly plus 1. Okay, so that completes the first part. Let's move on to the second part. All right, here is my second part, part B, 0 to 5, definite integral from 0 to 5, 1 over x minus 3 to the power 4 over 5 dx. Okay, so notice that on this interval, on the interval 0 to 5, this my integrand is not continuous. It is not continuous at x is equal to 3. Notice that x is equal to 3 in this interval 0 to 5. Okay, so I'm going to rewrite this integral as a summation of two integrals with the hope that I can write those two integrals as some proper definite integrals. So this is what I'm going to do. 0 to 3, my function x minus 3 to the power 4 over 5 dx, and then from 3 to 5, 1 over x minus 3 to the power 4 over 5 dx. Okay, now I'm going to use my definitions. Okay, this is the troubling point. 3 is the troubling point, so I'm going to use a symbol for that. I'm going to put a for this one and then take the limit of a. So this is going to be equal to limit as a approaches to 3 from the left hand side. Notice that I'm on the interval 0, 3, so a should be approaching to 3 from below. That means from the left hand side. Integration 0 to a 1 over x minus 3 to the power 4 over 5 dx plus integration, pardon me, I should have the limit as b approaches to 3 from the right hand side. I'm going to replace this 3 by b to 5 1 over x minus 3 to the power 4 over 5 dx. Okay, so we wrote these two improper integrals as a sum of two proper definite integrals. Okay, all right, here again I put this 3 plus, because if you are on this interval, if you replace this 3 by b, then your b should be approaching to 3 from above. So you need to have plus sign. All right, now we have set up these two proper integrals, proper definite integrals. Now we need to calculate those two proper integrals. Let's see how we can calculate that. Of course, we know how to integrate this function. By a u substitution, we can easily integrate this type of function. So let's integrate that. I'm not going to show the calculation here. I'll show you the answer, okay? Limit a approaches to 3 from the negative side. If you integrate this, this is what you are going to get. 5 times x minus 3 to the power 1/5. And then, of course, you need to put the limit 0 to a. And the second integration will be, again, 5 times x minus 3 to the power 1/5. Put the limit a to b to 5. The limits are going to be b to 5. Okay. Of course, I am forgetting the limit here. I need to put the limit here. Okay. Here I should have limit as b approaches to 3 from the positive side. Now all I have to do is to calculate this limit. Okay. Before I calculate, actually, I have to find the value of this one by evaluating this expression. This is in the evaluation notation. You plug in the upper and lower limits to find it. Limit a approaches to 3 from the negative side. If you find the evaluation notation here, you get 5 times a minus 3 to the power 1/5 minus, if you plug in the lower limit there, you get 5 times minus 3 to the power 1/5. That's the first value, first evaluation. The second evaluation, let's find the second one. Limit b approaches to 3 from the positive side. Here I plug in the upper limit 5 first, and then lower limit b. So that will become 5 times, if you plug in the upper limit, you get 5 minus 3, which is 2 to the power 1/5, minus 5 times b minus 3 to the power 1/5. Now, as you can see, as b goes to 3, this will become 0. Okay, so as a result, this is already 0, this is 0. You have only these two numbers. You can pull out a 5 here. So your answer would be 2 times this quantity. All right, that completes that example. Let's move on to the next example. Actually, I'm going to leave this as an exercise because it's very much similar to what we did in the first two parts. All right, here is the next theorem that I want to go over, theorem 5.23, comparison test for improper integrals. Okay, this is a very useful theorem that we can use to determine whether integrals are convergent or divergent. Okay, let's look at the statement of the theorem. Suppose f and g are functions that are continuous on an interval I. Here is the first part. If the improper integral of f on the interval I converges, and if g is between 0 and f of x. For all x in I, where the functions are defined, then the improper integral of g on I also converges. Okay, that's a very interesting theorem. This is actually intuitively, this is clear using graphs. Okay, you can see this intuitively using a graph. So here is the situation. Let's say your interval is a comma b. This is your graph f of x. I'm looking at the first part, okay? And here is your graph g of x. As you can see on this interval a comma b, let me actually write. This is your y is equal to f of x. This is y is equal to g of x. Okay. So in this interval, suppose that we are considering these two improper integrals. A to b f of x dx. And then the other improper integral is a to b g of x dx. Now let's go back to the statement of the theorem. If the improper integral of f on this interval I converges, and if your g is between 0 and f of x, of course it is between 0 and f of x. It is less than or equal to f of x, bigger than 0. 0 is this function. Then the improper integral of g on I also converges. If the improper integral of this function is convergent, then the improper integral of this function also should converge. Okay. So why is that true? What do you mean by this improper integral? What do you mean by this improper integral? That is the area under this curve, right? It's a positive area because it lies above the x-axis. And then what is this definite integral? That is the area under this curve. That is this area. As you can see clearly, this area is smaller than this area. Right? That means if this is convergent, this one should converge. This is convergent means this has a finite area. This area is finite. That means this area has to be finite because that area is small. That means this should converge. That's the idea. Okay. And then second part, if the improper integral of f on I diverges and f of x is between g of x and 0, for all x in this interval I, where the functions are defined, then the improper integral of g on I also diverges. Okay, what this tells you is that this time your f is between 0 and g, and we are given that if we know that f diverges, then g also should diverge. Okay, in that case, here is the picture. This time I'm going to change these labels. Okay, this time this is your g of x. G of x is bigger than or equal to f of x. This is your f of x. See, f of x is less than or equal to your g of x. This is a possible graph. And both should be greater than or equal to 0. Okay. Now, in that case, if you know that your f of x diverges, that means f of x diverges means if you look at this improper integral from a to b f of x dx, you know that it is divergent. That means it is infinite. So if this area is infinite, this area should be infinite. That means this improper integral should be divergent. So that's the idea, okay? But there could be different cases to consider, but this is mainly the idea of what's going on. All right, let's move on. Next, I want to work on this particular example. All right, let's read the example first. Determine whether each of the first two improper integrals listed here converges or diverges by applying comparison test with simpler improper integrals. For the third improper integral, explain why the comparison test with 1 over x squared does not give information. Then determine convergence or divergence by using limits of definite integrals. Okay, let's work on this one. Okay, we are going to use the comparison test for these two. Let's work on part A. Okay, let's work on part A. This is going to be 1 to infinity 1 over x times e to the power x dx. Okay, we need to determine whether this is convergent or divergent. So how do you do that? Here the whole point is you need to compare this given integrand with a function of this form, x to the power p. With p is some number. Okay, you need to compare your integrand with this function. And if you can compare this function with this function, then we know the convergence and divergence of this function from the previous theorem, theorem 5.21 and 5.22. Okay, we can apply those theorems to get the convergence or divergence of this one. Based on that, you can determine the convergence or divergence of your original integral. That's the goal here. Okay. All right, let's try to compare those two functions. Okay, these are the two functions that I'm interested in. 1 over x times e to the power x and question mark 1 over x to the power p. I need to determine whether I'm going to have a greater than sign or less than sign. So notice that from your pre-calculus class, we know that e to the power x is always bigger than or equal to x on the interval 1 comma infinity. On the interval 1 comma infinity, e to the power x is always greater than or equal to x. From this one, I can multiply both sides by x again, assuming that x is between 1 and infinity, to get x times e to the power x greater than or equal to x squared. Okay. Now, since both sides are positive, I can take the reciprocals of both sides by switching this inequality sign. Okay. So then we get 1 over x times e to the power x less than or equal to 1 over x squared. Now notice that that's what exactly I wanted. I wanted to compare this function against the function of this form. Now I have that comparison, of course, with the p-value 2. Okay, this value is 2. So let me go ahead and put that 2 there. So I have that comparison. This should be 2. And I know the comparison. What is the comparison? This question mark should be less than or equal. Okay. Now I can apply a previous theorem to determine whether this is convergent or divergent. We can use the comparison test. Okay. So I have a bigger function here, but I know by previous theorem that we discussed. Let's go back to that theorem. Yeah, right here. Okay. So if your p is bigger than 2, remember our p was 2. That is bigger than 1, pardon me. If your p is bigger than 1, then this improper integral converges to this particular number. Okay. So in that case, in our example, we know that this improper integral, this is the improper integral that we had in our example. X to the power 1 over x to the power 2 dx 1 to infinity. This converges by this theorem. Okay. So let's go back to that example. By theorem 5.21, by theorem 5.21, this integral converges. 1 to infinity, 1 over x squared dx converges. As you can see, the improper integral of the bigger function is convergent, then the improper integral of the smaller function should be convergent by the comparison test. By this test, the improper integral of g of x should be convergent if the improper integral of f of x is convergent. Okay, so we have the improper integral of the bigger function is convergent, so the improper integral of the smaller function should be convergent. So the conclusion is 1 to infinity x ex dx is convergent, or you can write converges. Okay, that completes the first part. Let's move on to the next part. Let's work on part B. Again, my goal is to compare my integrand with a function of the form 1 over x to the power p. Okay, so here is what I'm going to do. Okay, so notice that if I simplify my integrand a little bit, 1 plus x over x to the power 3 is equal to 1 over x to the power 3 plus x over x to the power 3, which is equal to 1 over x to the power 3 plus 1 over x squared. Notice that my x is between 0 and 1 because the limits of integral is 0 to 1. Okay, so x is between 0 and 1. That means these are positive quantities. Okay, so we should have this quantity is bigger than or equal to 1 over x squared. I'm just dropping this quantity. If I drop this quantity, I should get a smaller quantity, right? This is a summation. If I drop this off, I should get a smaller quantity. Now, as you can see, I have a comparison between this one and this function. Of course, this function is of the desired form, 1 over x to the power p. Okay, with the p value 2. Now, what can we say about this improper integral? First of all, notice that this is an improper integral, okay, because your lower limit is 0. At 0, your integrand is not continuous. What can you say about this integral? First of all, notice that this integral, this particular integral, integration of 1 over x squared from 0 to 1 dx diverges from theorem 5.22. If you go back to theorem 5.22, here is the situation we are in. If your p-value is bigger than or equal to 1, in fact, your p-value is 2 in this case, it is bigger than 1. In that case, this diverges. 0 to 1, 1 over x to the power p dx diverges. That means this integral diverges in this case. Okay, so as you can see now, the smaller integral, the improper integral of the smaller one diverges. So the improper integral of the bigger one should diverge by the comparison test. Here is your comparison test. Okay, if f of x diverges, if your smaller function is diverges, then the improper integral of the bigger function also should diverge. Okay, so that's what we have here. This is the bigger function. This is bigger than this function. We know that this function diverges. So by comparison test, this should also diverge. Comparison test. Integration 0 to 1, 1 plus x divided by x cubed dx diverges. Okay, that completes that part. Okay, let's work on the last part. Remember, for the third part, improper integral, explain why the comparison test with 1 over x squared does not give information. Then determine the convergence or divergence by using limits of definite integrals. Okay, let's work on this one. Let me copy that over here. First of all, notice that in this case, integration interval is 2 to infinity. That means your x is between 2 and infinity. If x is between 2 and infinity, this inequality is obviously true. X squared minus x has to be bigger than 0. Actually, this we can write even this is strictly bigger than 0. As you can see, if this is a number which is 2 or bigger than 2, then this quantity is clearly bigger than 0, and it is less than or equal to x squared, because you are taking x away from x squared, so that should give you a smaller number. Okay. All right, we have this inequality. From this inequality, look at this inequality. Okay, by taking the reciprocal, because both of these quantities are positive, you can take the reciprocal. Taking the reciprocal will give you 1 over x squared minus x greater than or equal to 1 over x squared. When you take the reciprocal, you switch the inequality sign. You can do this if numbers are positive, okay? Only if numbers are positive. All right, now, as you can see, can we use the convergence of this function to determine the convergence of this function? In this case, not, because by theorem 5.21, we know that by theorem 5.21, we know that the improper integral 1 to infinity 1 over x squared dx is convergent. This converges. So it is clear that the integral from 2 to infinity 1 over x squared dx also converges. Why is that? Notice that here the range is bigger than this one, and this function is positive. So this should have more positive area than this one. So if this converges, this should also converge. Now what do we have? We know that this particular integral is convergent on that interval, but this function is bigger than or equal to this function. If this function is bigger than or equal to this function, convergence of this function, this improper integral, does not imply that this improper integral of this function is convergent. If the function is bigger, you cannot compare that way. Okay. Of course, if this improper integral is divergent, you can clearly say that this is divergent by the comparison test. But in this case, you cannot apply the comparison test, because all you know is, you know that the improper integral of this function is convergent. Then you cannot say anything about the improper integral of a bigger function. Okay. It can be convergent or divergent because it's bigger. So you cannot use the comparison test with this particular function. Okay. All right. Next, we are asked to find this using the limits of definite integrals. Okay. So we can do that using limits of definite integrals. First of all, I'm going to write this integral 2 to infinity 1 over x squared minus x dx is equal to limit b goes to infinity, definite integral from 2 to b 1 over x squared minus x dx. Notice that even though my integrand is not continuous at x is equal to 0 and x is equal to 1, I'm not concerned about that, because my interval of integration is 2 to infinity. The 0 and 1 are outside of that interval. So this is the only bad number that I need to deal with via a limit. That's why I took this limit. Limit as b approaches to infinity. Definite integral 2 to b f of x dx. All right, now we can calculate this using, you can integrate this function using partial fractions. Limit as b approaches to infinity, integration 2 to b. The partial fraction decomposition for this one would be minus 1 over x plus 1 over x minus 1. Now you know how to integrate each individual function. So if you integrate those functions and plug in the limits, this is what you are going to get. I'm going to skip in some steps, okay? B approaches to infinity, you should get minus ln b plus ln b minus 1 plus ln 2 minus ln 1. Of course, this ln 1 is 0. ln 1 is 0. And now I can further simplify this using logarithmic rules. This should be equal to limit b approaches to infinity ln b minus 1 over b. The quotient rule for logarithm. Okay, if you have the difference of two logarithms, you can write that as a quotient, single quotient. Okay, plus ln 2. Now you take the limit as b approaches to infinity. What happens to this limit as b approaches to infinity? What happens to this quantity? Actually, view that quantity as 1 minus 1 over b. Then you will easily find the limit. Okay, this is nothing but 1 minus 1 over b, right? Now, as you can see clearly, as b approaches to infinity, this becomes 1. Okay, that means this becomes 1. That means you have ln 1, right? So this is equal to ln 1 plus ln 2, which is of course ln 2, because ln 1 is 0. Okay. All right, that completes our last example. With that, we conclude 5.6, section 5.6, and I'll stop there. I'll see you next time.